This is Talhan Biro from GeoSIG. I will talk about dam monitoring and systems associated with dam monitoring. In the background there is an image from a dam. This is the Merowe Dam in Sudan, and this is one of the largest dams in the world. As you can see, just at the end of the reservoir, the dam is a huge structure, and this structure is also monitored by GeoSIG equipment. We have hundreds of dams instrumented with our instruments worldwide, so we are going to give an overview about dam instrumentation. To be able to understand a little bit the instrumentation, let's have a look at major dam types. Dams are having different major types. One of them is an arch dam. Arch dam is made out of reinforced concrete structure, which is in front of the water, holding the reservoir back, and it is bent like an arch. That's why it's called an arch dam. They are basically holding the water back by the structure's properties, this arch structure, and they don't need really a huge space to be made. And then comes the gravity dams. The gravity dams, from the name one can understand that they are staying in place by the help of their own weight. They are relatively larger structures when compared to arch dams. They just carry on the pressure of the water that is retained by their own weight and the triangular shape of the body. And comes the embankment dams. These are the largest dam structures typically. They are made out of a soil structure. Inside there is a usually clay core that is impervious, and they are holding the water back with the help of this impervious core as well as their large mass in place. Of course there are several other types, but most of the types are a combination of those major types. So it can be a combination of gravity, embankment, or gravity and arch, and so on. But we are going to talk about these major types of dams today. Regarding the dams, we are going to talk about some features of the dams. We will tell you about the instrumentation options. Of course, when we are mentioning those, we are going to use some terminology, so I would like to show here what these are. If you look at the general view of a dam, first of all we see the body of the dam, which is this gray structure, and then comes the crest, which is the top part of the dam, and comes the foundations, which is basically carrying the dam itself on the soil that is sitting on. There are abutments, and comes the water retained. This is called reservoir. This reservoir, as we have seen in the very first picture, can be rather large depending on the type of the dam. Also, it can be a very wide area, or it can be a very deep reservoir. And upstream, where the water is coming to fill the dam, and downstream is the area where the water is actually trying to go to, but retained by the dam. And finally there is the free field. Free field is where it is enough far away from the dam or the structure itself so that the structure's own movements or own noise is not affecting any property that you will try to measure. So going to the next slide. First, maybe it would be nice to understand a little bit the typical factors that would influence the behavior of dams. In this figure, of course, we are seeing an arch dam, but this can also be any other type of dam. This is a conceptual drawing showing what kind of typical effects are happening on the dam from the water itself and structure itself, as well as ground motions, meaning earthquakes. So if you look at here, from the water, there is of course the variation of the water level. When it goes higher or lower, there are different stresses based on the hydrostatic pressure, and then the water temperature based on winter or summer is applying different kinds of pressures due to expansion and contraction. There will be as well the hydrodynamic pressures due to the movement of huge water mass behind the dam. There is an earthquake, which will exert also a lot of load on the dam itself coming from the ground. There is uplift pressure and pore pressures inside the dam itself from the structure. There is the dam's dead weight. This might cause, especially in embankment dams, settlements and so on. And we can also see here the abutment movements. This is also somehow due to earthquakes or semi-dynamic or settlement-based movements of the abutments. There is environmental effects. There is frost and thermal cycles in changes in the temperatures, humidity, and in the structure itself, the creep, the relaxation, if it is relatively new structure, curing of the structure, concrete itself, chemical reactions, and so on. Also on the downstream side, the pore pressures and the winter and summer temperature changes. After typical factors that can influence the behavior, we can look at a typical structural behavior of dams. In this slide, although we are looking at a typical arch dam, we could generally consider any type of dam having the same type of behavior. That is, for example, the one you see on the right hand side is the transverse movement of the dam structure. This is transverse to the center line of the dam itself, and as you can imagine, this is mostly caused by the water that is being held, the movement of that water mass, as well as the ground motions trying to destabilize the system. And then you will see on the left is a second mode. As you see, this is a in-plane motion of the dam, in a way torsional or rotational movements. So these two are the major mode shapes, structural behavior shapes of structures like dams. So based on this information, we need to understand what we need to observe in dams, because we are here to understand what to observe in terms of earthquakes that are acting and that are exerting forces on the dams. So first of all, we have to look at free field motions. Free field, as you might remember from my previous slide, is the point where it is enough far away from the dam structure itself so that the structure's movements are not affecting. And using these free field motions, we can characterize the affecting earthquake on the dam or on the area. By understanding the earthquake, we can find out, of course, the amplitudes, the duration of it, the frequency content, so we can understand what is the effect, and we can define the input motion to be able to understand what is happening in our structure because of this input motion. And after that, there is abutment motions. The abutment motions, as we have seen before, the abutments are where the dams are relying on. So basically the movements in these abutments, or the earthquake wave that is coming from these abutments, they are all transferred to the dam somehow. So we can define this earthquake wave propagation to the dam from these motions, as well as we can determine the soil structure interaction, which means the interaction of the structure with the soil that it is built on, and what kind of a reaction is the structure is showing, and how much of it is again exerted back to the soil itself, to understand this interaction. And then of course comes the response and the characteristics of the dam itself. Basically we need to of course observe what kind of a response our structure is giving to the input motion or the exerted forces, so that we can understand how it is moving, how it is behaving, whether there are any failures and so on. So we can also define the modal parameters, which are the modal frequency, the modal damping, and the modal shape, which we have seen, I think, one slide before, so that we can understand how our dam is behaving under the input motion. To be able to observe all this, we need to utilize strong motion instrumentation. And what to utilize, we will just go over this. To be able to cover all the motion and the forces coming, we can use 3-component accelerometers, which we call also triaxial accelerometers. These can range from 10 micro-Gs up to 2 Gs, and then from 0 Hz, in other words DC, to 100 Hz frequency range, so that we can cover comfortably all the motions that might have effect on the dam, and then all the motions that the dam is showing as a response. From these accelerometers, the signals need to be recorded, so digital recorders need to be used with a suitable dynamic range, amplitude range, and a good sampling rate, so that we can record the corresponding sensor. And then there has to be an accurate time reference. This time reference can be either local to each recorder, or it could as well be distributed from a central reference. And to be highly accurate, this can be based on GPS. Then we have to, of course, consider the trigger capabilities, which means how to detect if there was a seismic event. We can use level triggering based on a level threshold, and then short time average, long time average processing, where average of the amplitudes during a short time are highly exceeding average of a long time. Plus, it is highly desirable to have a common trigger, whereas all the recorders are able to record the same event at the same time. Of course, recording requires local or central data storage. Somehow the data has to be stored to be able to analyze or visualize later. And such storage can be either local or at a central or remote location. This remote location can be either in the dam, remote from the measuring points themselves, or it can be even much further away. So there can be communication links for the downloading of these recordings to a central site. This can be done either by wires on landlines or wireless links. And of course, we would desire to be able to control these units and remotely configure all the functionality, test and see the state of health. And finally, we of course need a software that will help us to analyze all the data and archive it and properly keep it for our records. Now let's go into recommended topologies of structural strong motion instrumentation in dams. We are going to present this in terms of the major types of the dams. So we will start with the arch dams. As we have seen also before, arch dams are rather delicate structures when compared to other types, and certain care has to be taken in terms of their structural properties. We are going to, of course, tell here about typical implementations. If you look at a typical arch dam, we can understand the input motion and dam response from positioning instruments at the locations depicted by the letter A. So with this kind of instrumentation here, we will be able to see what's going on at one of the abutments and at the foundation of the dam, as well as at the crest of the dam. This way we will be partially able to see the motion we have already seen before in the moving pictures, that we could at least determine some part of that. Not all, but some part of that. And then comes, of course, the complementary part to that. If we were able to install instruments on the other side of the crest, then this would be complementing, at least giving us the possibility to understand the crest motions much better. Then comes, of course, the very important free field motion instrument, which is the letter C. As you would see here, this free field is defined for this kind of dams, arch dams, is from 1 to 2 times of the dam height. Basically then we can relate it to the size of the dam this way. There are also other positions that we can install instrumentations, and these will basically complement our measurements. And then as you see, if you put devices on F, then we will be able to see the wave propagation which we were talking about before regarding the motion transfer from the abutments or foundation to the dam itself. Here, when we look at this picture, the major concern we should have is to be able to instrument the A, B and C points so that we can define a proper response of the dam, and in addition to that we can also consider the letter E. Gravity dams are made out of not only a single piece, they are usually made up of different cross-sectional segments, and this enables the possibility of construction due to the reinforced concrete and the pouring and curing of that. It has a crest instrument, foundation instruments, as minimum base and crown response or crest response, and then comes the free field. You will see here again 1 to 2 times the dam height. Therefore we will be able to add the abutment motions with E. So basically from this picture we can also say that a desirable instrumentation is from the letters A, B, C and E. If we go forward to embankment dams, these are, as we have mentioned before, the largest structures. Of course their motions are as well different. So for this kind of dams we would need to have the abutment motions. For the dam response, these are the important motions we are interested in, and these are achieved by instrumenting A and B points. Then of course we will have to have a C free field motion, as you will see here. Since these are rather large structures, not only by height but also as well in the cross-sectional width, then we need to go up 3 to 4 times of the dam height to be able to achieve a proper free field instrumentation. In this one also the desirable instrumentation is A, B, C and D. Those were the recommendations based on the scientific studies. And as far as the practical implementations are concerned, we can also refer to a more practical institution. This is in the United States, that is called COSMOS, Consortium of Organizations for Strong Motion Observation Systems. This consortium, based on all the practical applications, recommended the sketch we see over here, whereas this is very much similar to what we were saying in each type, where we should put the instruments at the crest, on the abutments, in the midsection and foundation, and finally 3 to 4 times or similar distance to be able to find out the dam response. And finally we can actually summarize what we have seen. To be able to achieve a real proper dam instrumentation, our recommendation to have instrumented in a dam are the crest in the middle, in the quarter another instrument to be able to see the torsional behavior we have seen earlier, and then the motions of the abutments, mid-body section, in the galleries, especially in gravity and embankment dams, and then one in the foundation level and one in the free field. So basically this will constitute about 8 to 9 positions to be monitored in a proper and well-designed dam instrumentation topology. Let's see what we can offer for this kind of instrumentation. GeoSIG has different types of instruments that can be used in dams, and one of them is a centralized approach. Basically, in a centralized system there is a central recorder, and the central recorder is receiving all the data from the sensors that are distributed along the or inside the dam. This kind of recorder does not need interconnection meaning the connection or awareness at each position from the other one. Basically, in any case, the central recorder will be taking all the data in one central location. There is no need to have some sort of a connection between the monitored nodes. And as we said before, all the data will be available at one location. This is one of the major advantages of central recording. And in addition to central recording, actually it might in the future be expanded by adding individual stations that are linked to the network center itself. And what we are supplying, what we are manufacturing for this purpose is the GMC recorders, GNC recorders, and CR5P recorders. Before going into those ones, we can just have a quick look at the options A and B as we see on the sketch. The option A actually is consisting of digitizer and recorder pairs implemented in the central recorder. The sensor data is directly coming into this section and then it is being digitized and recorded in this module. This recorder, this central recorder, is able to communicate with the outside world through different types of communication medium. It can be modem, landlines, internet, Ethernet, and wireless, and all sorts of other available communication methods. The other type, option B, it's again of course a central recorder, but this time the recording is taken over by a computer that is dedicated for this purpose. So basically the sensor data are incoming to a digitizing module, and from the digitizers it is transferred to a computer-based central recorder, and this computer is able to communicate with the outside world for the data acquisition and system intervention. Then comes the decentralized solutions. We are talking about individual recorders that are distributed next to or at measuring points together with the sensor. Of course, in this case there will be an interconnection which we will cover after this slide, what all this mean. But then there are features in this decentralized solution is that the data is stored at each measuring point. There is, instead of an analog cable coming from the sensor to the central recorder, there is only a digital transmission, because the recording and digitization is happening at the measuring point. So in any case there is a need to have a communication means, usually achieved by cable in the dam structure. For this kind of recorders we have GSR systems and GMS, the newest systems that are available to be used in different topologies. So again, if we go into each option, the option A is what we call CCL, which means common time, common trigger, and local communication. So basically with this kind of connection, or what we call it as interconnection, we will have a common time that is distributed to each recorder, each measuring point, and then a trigger information in case any recorder, any digitizer is triggering due to a level exceedance. Then all the others will know about this and start to record at the same time. And then communication is achieved by visiting or instrumenting each and every recorder separately to be able to interact with the unit. For the option B, this is called CCC, and there is again the common time, common trigger, but this time central communication. So the communication is achieved by a central module via which one can connect to each and every measuring point, every recorder, to be able to retrieve the data, make configuration, and so on. Of course, in the meantime, one can also do at each location individual link to each station. And finally, more advanced solution is the CCM, and this one is a common time, common trigger, and then multi-node communication. Basically, the multi-node communication enables us to be able to connect to each and every recorder from each and every recorder. So basically, when you go to one of the points, then you will be able to connect to any of the other points. So this is a more complex mechanism. Going back, we can correlate a little bit also with what we are offering, all these options. The GMC is, as I said before, one of the newest instruments we have. This is a central recorder. It is based on, again, this GMS Netquakes technology that is available. and it is made up into a central system, is the GNC. This is again similar to GMC, but it is depending on the GSR topology. One of the very versatile systems we have, the CR5P, and this one is a computer-based recorder which is very modular, very highly customizable in terms of implementation and usage. And this is based on computer recording, having digitizer modules, and each digitizer module is then connected to a computer, either embedded in the system or it can be an external computer. This is a very versatile and state-of-the-art system. Going to the individual recorders, we have of course the good old GSRs, thousands of them being used at the moment around the world, and also in dams. So this is available in all the options we have seen before. And then comes the latest technology, the Netquakes GMS recorder, which is also available in different communication options to be able to use in dams. It may as well be quickly implemented into TCP/IP Ethernet networks with wireless possibilities, so it has a very wide range of application. Worldwide there are more than 33,000 dams. This is a significant amount of structures around the world. And in this picture we are seeing the countries having dams, and these are only showing the dams that are having a height of 50 meters and a crest width of 100 meters. This picture shows us the extent of possibilities in this industry. When we look in GeoSIG experience over the years, we can see we have a long list for dams. Actually, in this picture we see that is going up to 2009 with 160 plus dams. So we are in year 2011, and actually we have at the moment 200 or a little bit more dams that are instrumented by GeoSIG instruments. The world map is also showing the extent of successful GeoSIG instrumentation around the world. You can see all this information and many more other information in our website. On the website you will be able to find out example applications as well. If you go to projects menu, and then you can choose any other topics as well, but if you go to the dams, then you will be able to see this example. This one is a exemplary dam in Iran. It's a Karke dam. It's one of the larger dams. It is a good example, especially for distributed or decentralized application, which has 6 measuring points, 6 digitizers, and having an interconnection system which has been working several years now, more than I think 10 years at the moment, with no problems. So you can find, of course, in this web page more information on this application, and you can also find a link to the official project Karke Dam website, where you can find more information, especially about the dam itself. This presentation is based on several documents and references available also publicly. I just wanted to list those references for your information and for your reference as well. This is not, of course, all the references available. There are hundreds of others, but just wanted to list here the ones that we were mostly referring to. I hope all this information was useful, and I would like to thank you again very much. Thank you.